So welcome you back to this module. So last module we discussed one result which talks about the asymptotic properties of maximum likelihood estimator. In fact, it talks about asymptotic properties of the root of a likelihood equation. So let's try to revisit that result, because that result is very important. It speaks a lot about maximum likelihood estimators in certain situations. So the result was as follows. Suppose A1, A2 and A3 hold. So let me write down first. Suppose A1, A2, A3 hold, and Lx theta is a differentiable function of theta. So I am taking my theta to be a subset of R almost everywhere. That means the set of all those x's where Lx theta is not differentiable, that has a measure 0, or probability of that is 0. Then there exists a sequence theta n hat star x. So let me write down theta n star such that there will always exist a sequence theta n hat star such that what happens? That this theta n star is a critical point. That probability goes to 1 as n goes to infinity, or in other words, limit n going to infinity. Probability theta naught Lx prime theta n hat star x is equal to 0 is 1. So probability that theta n hat star x is a critical point, that probability goes to 1 as n goes to infinity. Second thing is, as n goes to infinity, probability that this theta n hat star x is a local maxima, that probability is also 1. A local maxima. Third is, this theta n hat star x would be consistent for theta. So theta n hat star x converges in probability to theta naught. And where theta naught is the true value of the parameter. So this is the result which we proved, which was slightly technical in nature. At least I gave you the brief outline of the proof. But let us try to see what are its consequences. The first consequence is, if this likelihood equation Lx prime theta is equal to 0 has a multiple roots, what it says? There will always exist a sequence theta n hat star x such that limit n going to infinity probability theta naught p theta naught Lx prime theta naught x star is equal to 0 is 1. So among them, most likely there will always exist a sequence which is of critical points such that such critical points is a local maxima, and theta n hat star x always goes to theta naught. So in case of multiple roots, you have to identify various critical points of the likelihood equation and then try to look at where is the local maxima. Among all of them, one will be local maxima. You have to identify the one corresponding to the local maxima. But when for every n and x, this equation has a unique root, then this theorem suggests that such a solution would be the maximum likelihood estimator, and not only that, it would be consistent. So let me write down that in the form of a remark. In case of multiple roots of the equation Lx prime theta is equal to 0, the above theorem does not say which sequence of roots of the equation should be chosen. sequence of roots of the equation or which sequence of the roots should be chosen. To ensure consistency. So what you know is among all such there will be one which will be consistent. Now the above theorem talks everything in terms of limit n going to infinity. So for a fixed sample size n, it does not talk about the existence of a local maxima. So the above theorem, because everything is in terms of a as n goes to infinity, it says as n goes to infinity, this would have a critical point. So the above theorem does not guarantee that for any given r, given n, however large, the likelihood function has any local maximum. See, if for every n and x, the likelihood equation has a unique root, if for every n and x, Lx prime theta is equal to 0, has a unique root, then you know that Lx prime theta, theta and x equal to 0, and that is unique. Then the above theorem guarantees that it will be consistent and probability and with probability tending to 1, it will maximize the likelihood. Now one can prove similar result for more than one dimensions under certain regularity conditions. So under certain regularity conditions, the above result can be extended to the case when theta is not a subset of R, but theta is a subset of Rk. So that we are not going to do over here. So this part which I have written over here, that if you want, you can write down that as a corollary. Which says that if for every n and x, This consistency, actually, the proof of consistency, if there is a unique root, this proof of consistency is contained in the proof of the last theorem. So, under the assumptions of last theorem, if Lx prime theta is equal to 0, has unique root for each n and x. So unique root you can write down as theta n hat x. Then theta n hat x is consistent for theta. That is, this proof is just essentially contained in last one. Moreover, with probability tending to 1, theta n hat star, theta n hat x maximizes the likelihood function. Now, this proof is contained in the proof of last theorem. So, let me not go over it, you can just complete the proof. Now, I'll do another result on asymptotic properties of maximum likelihood estimators. This property says that suppose your f theta x is such that it is 3 times differentiable, and its third derivative is bounded by a function mx which is integrable. That means its expected value exists. If that is the case, then for any consistent sequence of estimators theta n hat star, which is also a root of Lx prime theta is equal to 0, you would have a asymptotic normality. So that result is very important in the sense that if you certain regularity conditions are satisfied, which are essentially in terms of existence of a third derivative, and third derivative being bounded by a function mx whose expectation is finite, then if you have a sequence of estimator theta n hat star, theta n hat x, which are the critical points, that means Lx prime theta n hat x equal to 0, and they are consistent, then root n theta n hat x minus theta naught would go in distribution to normal 0, and variance as 1 upon the information matrix I theta. Information, here there is no matrix because theta is real. So that result we'll do next time, because it's again going to take at least 30 minutes to complete that proof. So that I'll do in a standalone module, which would be sometime in one of the, in fact, which would be in the next module itself. So that's all I have for this module. So see you in the next module, where I'll prove the asymptotic normality of certain variants of maximum likelihood estimators. Thank you.